Now, in this video, we're going to talk about probability distributions. Now, there are basically two types of probability distributions, all right? The discrete and the continuous. Now, we'll be, focusing on the discrete probability functions or the discrete probability distribution rather. Okay, now what is a discrete probability distribution? Now, all right, in simple terms, a discrete probability distribution is a complete list or mathematical rule that shows every possible outcome of a countable event along with the exact chance or probability of each outcome happening. Now, I rather or simply put it as you know, it's a distribution that describes where outcomes are countable and each possible value, has an associated probability, let's say 1, 2, 3, or either yes or no. All right. For example, the number of heads in a certain number of coin toss. For example, you can get one head. If you toss a coin twice, thrice, you cannot get 1.5 heads, 2.2. So we can see that these outcome are discrete. Okay, they are distinct, they are countable. All right. Now, um let me quickly shed a little bit of light in on continuous probability. All right. Now, continuous probability distribution describe random variables that can you know take you know infinitely many values within a range. For example, if we were to um take at or we look at the values of specific heights of people in a class, right? We can get values like 1.5, 1.51 meters, we can get value like 1.72 and so on and so forth. So we can see that these values are confined within a range. They can take you know infinitely many values, all right? But if we were to, let's say toss a coin three times, you cannot get, four heads in a coin toss of three. You understand? So we can see that it is this discrete. You cannot get you know, 3.1 heads, 3.2, that you understand. So we can also see that it is countable for discrete probability distributions. All right. All right. So yeah. A discrete, probability distribution has, various types. But in this lesson, we are going to be, we're going to focus mainly on the three main types, right? Which are the binomial, the geometric, and the Poisson's distribution. Okay. Now, the binomial distribution. Now, this is, it is a specific type of discrete probability distribution. Now it calculates the likelihood of getting a specific number of successes in a fixed number of independent trials, where each trial has only two possible outcomes. For example, let's say we toss a coin, all right. Now it's either we get a head or a tail, all right. Same applies when we really die. It's either we get a one or we don't get a one, all right. So we it deals with the likelihood of getting a specific number of successes, all right, in a fixed number of independent trials. So like, when we talk about independent trial, we just talk about tossing the die or tossing the coin three times, four times, you see how many hits you get after tossing this coin after a specific number of times, how many successes is the number of heads or the number of tail you get, after tossing this coin. Same applies for a die, how many number of successes you get, as your number showing as one after rolling the die. You understand? So yeah. Each trial has only two possible outcomes, either a success or a failure. You understand? As I explained earlier, you can either, have successfully land a head or, fail in doing so. Same applies to when you roll a die. You can either successfully, land on a one or you don't, which is a failure. So let's quickly, shed more light on this binomial distribution and probably we get to our formula. So yeah, as explained earlier, in a binomial distribution, we have only two possible outcome, a success or a failure. Now let's say I flip a coin two times. All right, and I want to find the probability of flipping a certain number of heads. All right, so we can say that we can let this number of um heads be x. All right. Now the question says find the probability of flipping zero heads, one and two, all right, respectively. Now we can use our binomial you know distribution from what we know, right, to find out our certain probability. All right. Now we know that um you know number of times we flip, can say let this be n is two. All right. Now let's find the probability of flipping zero x. Okay. Now when we get zero x, all right, remember there are two trials. All right, we are flipping the coin two times. Is either fail we fail on the first try and we fail the second try. All right. So remember there are only two possible outcomes, the success and the failure. Now, if we were to get zero heads, from flipping this coin two times, we fail on the first try and we fail on the second try. All right. Now the probability of failing is, let's denote this, the probability of success, let's denote this as p, you know and the probability of failure, let's denote this as q. All right, where p plus q is 1. All right, success and failure, so they can either be success or failure, and that um from your law of probabilities. When you have two events, that are um mutually exclusive, this sum of the probabilities is 1. All right, so let's quickly skip that part. Now we know that the probability of from here, the probability of a failure is, we can denote that as q. All right, pattern amount rating, and on the second try we also failed. All right, so we can just multiply, get q's pattern amount rating here. All right, so that just q square. Now we want to find the probability of flipping one eight. All right, so now for us to get one head, see that we fail on our first try and succeed on our second try. We fail on our first try and succeed on our second try, or all right, we succeed on our first try and we fail on our second try, and we know that we can set our failure to be q and set our success to be p. All right, or so now this is the probability of getting one, flipping one eight after you know flipping a coin twice. So let's quickly do the last one, which is probability of yeah. So let's quickly move to the last one. Probability of getting to it. We know that for us to get to it, we should be succeeding on the first try and succeeding on the second try. There is no other possibilities here. All right. So success is denoted as P, and success on the second try is denoted as P. So we have P square. All right. All right. Now, before I forget to say, the sum of all possible probability um in a binomial distribution is one. All right. The sum of all possible outcomes in a binomial distribution is one. Now we from what we did earlier, we know that the probability of keeping zero heads was q square. All right, one heads was 2pq, right, and two heads was p square. From this we can compute, we can test if the sum of all these is one. All right, so let's quickly check that. It's q square plus 2pq plus p square. All right, now we know that this is same as p plus q square. All right, now we know that from what we did earlier that p plus q is simply one. So this is simply one square, which is one. So this proves our thesis that the probability of all possible outcome in a binomial expansion is one. Now, yeah, now from our previous calculations, just quickly write down our terms. Alright, know that this is q square, this is other man writes in again. Alright, alright. Now we know that the number of times we can denote this as n, number of trials. And a number of outcomes, let us denote this as k, where k is also x. Alright, this is number of outcomes. Now you remember from your permutations and combination. Alright, from your permutations and combination, when you are trying to choose a certain number of stuff from a particular number of selection. Alright, you can denote this as n choose r. Right, now in this our case, we can represent r as k, because we can just see that how many times are we getting k from n number of times. All right, now if we look into this closely, we see that this right here follows a pattern. All right, now what is the pattern? Now we can first write down our combination, right, and choose k. Now we know that um P is the denotation for the probability of a success. Now we can see that this first probability here has no value for P. So we can simply just denote that as one. And what value of P can be one, we can see, pardon my handwriting, we can see that this is to the power of zero. Yeah. Now now for the Q value, we see that the Q value has the power of two, right? Now we can see that the Q is to the power of two. Now let's move to the next one, right? Still an N, choose key. We see that the P has a power of one, right? And the Q has a power of one, right? Let's move to the third one and choose key, where the P has a power of two and the Q has a power of zero, right? Now, from what we noticed here, we see that adding these two here, here gives us the value two, and we know that two is the number of trials, all right, and the number of trials is n, so we can simply replace this n as two. Okay, now for our k, we simply know that k is just the number of outcomes, all right, and we can simply denote this k as for the first to be zero, all right, for the first, for the second to be one, and for the third to be zero, all right. Now I've simply just put down the values for each of these n, all right. Now pardon, let me just simply make this um let me simply just make this neater, all right. So we have n, choose k, all right. We have p for the first and q. Now we know that the sum of the value here and let's say the value here is n. Now can we express this value here as um x and n term, all right. So we know from collecting like terms that y is n minus x, all right. So we can simply just solve this into here. We have something like this then, all right, where x is your k, remember. Then sorry, this should be p, all right. X is simply your k and q is n minus, as simple as this, all right. So we have simply formulated our um formula for the binomial distribution, and let's quickly verify this. Now from the first value we have q squared, right? Now subbing in from our formula and choose k, p to the power of k, q to the power of n minus q. Now subbing in our values, we know that n is always 2, which is the number of trials, all right. K in this case, which is the number of outcomes, all right, is 0, right. Now p to the power of k, which is 0, q to the power of n minus k, which is 2 minus 0, which is 2. We know that this is 2 choose 0, all right. 2 choose 0 is 1, all right, or 2 combination 0, which is 1. p to the power of 0 is 1 and q squared. So we can say that this relates to this. Now let's try for the other, you know, for the other scenarios. All right. So let's try for this. All right. 2pq. Right. Now let's see if the follows our, you know, formula of binomial expression. All right. Binomial distribution. So this is the formula here. So let's quickly, plug in our values. So we know n to be 2 as a number of trials as always. Sorry, pardon, this should be k. Alright, this here should be k. So we know that our k in this case is 1. Alright, the number of outcomes. So we have p to the power of 1. Alright, q to the power of 2 minus 1, which is 1. Alright, we know that 2 combination 1 is 2. P to the power of 1 is p. Q to the power of q. So we know that this, you know, it's the same as this. So let's quickly, try for the last one. Let's see if it's actually correct. Now we have p square, alright, and we have from our formula, right? Now, as always, n to be 2, right? You k to be 2, which is a number of outcomes, p to the power of 2, q to the power of 2 minus 2, which is 0, right? 2 just 2 is just 1, p square, and q. So q to the power of 0, which is 1, rather. Alright, so we have p square. So we know that this same as this. So this just verifies our formula for the binomial distribution. Simply just simply write this down. Yeah, this is all right. So let us quickly use our values to plug in and get our probabilities of these periods events. From the first, we know that probability of getting a 0 is q squared. A 1, and a 2 from two number of trials. Now we know that q is the probability of a failure. Okay. Now probability of a failure when of failing when tossing a coin, of failing and getting ahead rather than when tossing a coin, we know it to be half. All right, which is 1/2. So this should just be half squared. All right, and we also know that similarly the probability of a success is half. All right, so this should just be 2 half times half. All right, which is half. And same goes for this last one, which is half squared. So now if we were to sum our individual probabilities, we end up with a sum of 1. So this just proves our formal definition of this sum of binomial distribution being equals to 1. Okay, the sum of each individual possible outcomes. Okay, So let's quickly, do with something more complicated. Now, let's take a question. A student is, you know, taking a 10 question multiple choice quiz. Now, each question has four options A, B, C, and D, and only one option is correct. Because the student did not study, they decide to guess the answer to every single question completely at random. Now, let us, find the probability that this student gets exactly, let's see, 7 answers correctly. Now, from our formula for the binomial distribution, we can simply, compute this as fast as possible. You know, now we know that n is a number of, options, number of questions rather. Sorry, n is a number of questions. All right, so n is 10. Choose. Now, k is a number of, answer that is getting, is to get correctly. All right, so let us denote this as 7. Now, the probability of the success. Now, since there happens to be, 4 options, he has a 1 out of 4% chance in, getting that answer correctly. All right, if he is to choose at random. All right, so we can just, raise the power of k, which is 7. Then q is the probability of, you know of failure. All right, which is he has a 3 out of 4 chance of, failing if he chooses an answer at random. All right, then we have 10 minus 7, so let's just note this as 3. Now we know 10 choose 7. We can just do something like this times 9 times 8 times 7 factorial over 7 factorial. Alright, so yeah, 7 factorial, 7 factorial, pardon, yeah, 7 factorial cancels this, and yeah, just compute your values for everything here and you get your answer. So yes, we can, simply just use this binomial distributions to, calculate probability of discrete values, where n is just number of, selection, and k is, the number of items that you are choosing from, or that you are going to choose. But I come again, n is just, the number of, items available, and k is just the number of items you are to choose, right? And p is just the probability of the success, and q is, probability of the failure. Well, in this case, there is only 4 options, all right? So if this case, randomly, each probability of, picking a correct answer is just 1 out of 4 options. And in a similar case, the probability of the failure of in failing that, particular question, if he is to choose randomly, is just, 3 out of 3 out of 4. So we simply just plug in our values and, simply compute, probabilities for these type of, questions and variables. So yeah, let's just quickly give this close, and I'll see you in our next lesson.